An insurance company determines vehicle insurance premiums based on known risk factors and then charges accordingly. And interestingly, one of those factors is the color of your car. The insurance company believes that people with some color cars are more likely to get into accidents. And so, to research this, they examine police reports for total loss collisions, and they find this data. And so this is what's called a frequency table. And we're working here with categorical data, or in other words, qualitative data, data that is categories, but it's not numerical data. And so this frequency table tells me that there were 25 reports that involved a blue car. And so from this large collection of reports, the frequency or the count of reports for each of these colors was recorded. And that's what a frequency table is. And so the first thing we're going to do is try to create a graphical representation of this data. And first one we're going to do is called a bar graph. A bar graph is reasonably simple. The idea is we have a horizontal and our vertical axis. And along the vertical is going to be our frequency. Actually, let me write this a little differently. I'm going to actually try to write it sideways here. Frequency. I didn't write that very well. Okay, and then we're going to create bars for each of our colors. So this vertical axis is going to be an actual numerical axis, and it's going to have to go up at least past 50 in order for me to be able to fit all this data in. So I think I'm going to go 5, 10, 15, 20, 25, 30, 35, 40, 45, 50, and then I'm going to need to go at least one more, so there's 55. And I'll go ahead and toss 60 in here. So now we can draw a bar for each of our colors. So our blue cars have a frequency of 25, so I'm going to draw a bar, and that bar is going to have a height of 25, right? And so this is going to correspond to blue cars. So now I'm going to draw a bar for green cars, and it needs to have a height of 52, which is right around here. And I'm just sort of estimating here. Typically, software packages like Excel is a common one, or even something like Google Docs is used to create these graphs rather than trying to draw them by hand. But for the sake of illustration here, we'll go ahead and we'll try to draw this by hand. And so there's our red cars, which have a height of 41. And then you would continue this on for the other colors. And our resulting bar graph will look something like this. Now, you can tell that it's kind of hard to tell where the where the bars are here. And so one solution to that would be to put in grid lines, which would look something like that. And put those every 5 or 10 spaces. So that'd be one option. Ooh, I did not mean to do that. Hold on, there we are. So that would be one option for dealing with the for dealing with this issue. There we go. Good enough. Another option, and probably a little simpler, would be to just put at the top of each bar what the corresponding frequency is, and that way somebody reading the graph could easily identify the frequency of each of the bars without having to look horizontally. Now, the advantage of the graphical display, of course, is that it makes it very clear visually what the relative sizes of these quantities are. And so this would be a bar graph for categorical data. So this was a bar graph for this frequency table of car colors. So now we're going to try to create something called a Pareto chart. Now, a Pareto chart is really the same idea as a bar graph. It's just a specific type of bar graph. So we're going to start it the same way. 5, 10, 15, 20, 25, 30, 35, 40. Now, of course, if I really wanted to do a really high-quality graph, I would not just be freehanding this. I would be using some either graph paper or use a pencil, or, like I said, use a computer. But this will be okay for now. So the idea of a Pareto chart is that we're going to do a bar graph, but we're going to arrange the bars in decreasing frequency order. So in other words, we're going to put first, the first color we're going to draw, or sorry, the first bar we're going to draw is for the category with the highest frequency, which is 52 here, for the green cars. So that's our green cars. And then our next highest frequency appears to be the red cars with a frequency of 41. And so we could draw in our red car bar. And then next one is our black cars with a frequency of 39. And so on. And there's our completed Pareto chart. Now, the advantage of a Pareto chart over our original bar graph is that here, at least without the numbers listed, it would have been hard to tell the difference between, say, the red cars and the black cars. But by creating a Pareto chart, you can, the bars that are similar height are going to be right next to each other, and so it's easier to see the difference between the heights. So, sometimes we're interested in not so much the size of each of these categories, but rather their relative sizes. And so we're going to talk about relative frequencies, and then try to create a pie chart. So first thing we're going to do is talk about relative frequencies. And so this would be computing the percentage of all cars that fit into each of these categories. And so first thing we need to do is add up our total frequencies. So let's see, if I pull out my calculator and add these up, I get 216 is the total number of reports that were read. And so the relative frequency is what is the percentage. So 25 out of 216. So that would be 25 divided by 216 comes out to be about 0.1157. or about 11.6%. So that means 11.6% of all of these reports were blue cars. We could do the same thing here for green cars. 52 out of 216 is about 0.2407, or about 24.1%. And we could find the relative frequencies for all of these colors. So I'm going to do that real quick. And there's all of our relative frequencies. So the idea of a pie chart now is that we're going to create a graph where we have a circle that we're going to divide up into pie slices. And so the idea is that the size of a pie slice should correspond to the relative percentage. So for example, if I saw a slice like this, that looks like it's about a quarter of the circle, so that should be about 25%. Now, if you're getting really technical here, and want to very precisely create a pie chart, you can take each of these percentages and multiply it times 360 degrees. Well, of course, you would need to convert the percentage into a decimal first. And if you do that, you would come up with a number of, it's about 38 degrees. And then you could use a protractor to come up with the graph. But the reality is that most of the time people don't bother doing that anymore, because, we usually use computers nowadays to create pie charts. But just for the fun of it, let's see if we can freehand one pretty close. So I'm going to start with the green here, because 24% is awfully close to 25%. So I would expect that to be just slightly less than a quarter circle. So that's my green, which is, 24%, well, 24.1%. Okay, so let's maybe go to red now, because red is going to be 19%. And so that's going to be even less than 25%, right? Let's see here. If I divide this into 5 pieces, each one would be another 5%, so it needs to be about 1/5 less than that. Okay, so maybe like that. Let's call that red, and that's about 19%. And then white is going to be 18%, so that's going to be even a little bit less than that one. That's pretty good. I know that's not white, but white wouldn't show up not very well now, would it? And so we got about 16.7% there. And black is going to be similar, but a little bit bigger than white, a little less than red. So maybe right around there. So we'll call that black, and that one's 18.1%. And now we have blue and gray left, both of which are going to be, let's see here, gray is going to be about half of that one. So, let's go with that. So there's blue, 11.6%, and then we got gray here with 10.6%. Now this is a pretty lousy pie chart. Like I said, we'd be a lot better off using a computer, but at least you get the idea of how we form a pie chart by hand. The idea is we want the relative proportions, percentages of the circle, to correspond with the relative frequencies of our data. So here's a slightly nicer looking pie chart that shows the percentage of voters supporting each candidate running for a local Senate seat. So we can see here that Douglas has 43% of the voter support, Reeves has 11%, and Ellison 46%. So if there were 20,000 voters in the district, about how many voters would be supporting Reeves? So to answer this question, we're going to use our percentages here to help us out. This is telling me that 11% of voters are supporting Reeves. So to find 11%, so we want 11% of the 20,000 voters, we just need to multiply 20,000 times 11% written as a decimal. So we're finding 11% of 20,000, which is about 2,200 voters. So it's really easy on a computer to do all kinds of cool graphics, graphical displays, but that doesn't always mean that you should. So we're going to take a minute and talk about some bad graphical representations of data. So here is the car color data we were looking at earlier, and here it's done in a 3D bar graph. The problem with this graph is that because of the perspective of it, it's almost impossible to read now. I mean, it's really hard to tell which of these bars is actually larger when it is on this slant like this. And so this is really a bad graphical representation now. It's really hard to read. Now here's another situation. So suppose a labor union produces this graphic designed to show the difference between the average manager salary and the average worker salary. Now, it could be, I mean, if I was to look at this, I'd say, okay, if I was to imagine this as, you know, the worker salary, then let's see here, that, ooh, wow, this one's like 4 of those. And so if I was to look at this, I might think that, wow, those manager salaries are 4 times bigger than the worker salaries. But it's sometimes hard to tell, because not everyone, you know, does things that way. It could be that the manager's salaries are only twice as big as the worker's salaries, and the you know, the person creating this representation said, "Oh, look, it's only twice as big," right? And so that visual distortion of area versus a length really makes this hard to tell based on the graphic what's really going on. So this type of pictogram is not a good representation. Now there are some representations where, say, you would use like some kind of picture, like a dollar sign to represent money, and then you use a certain number of them to represent relative sizes, and that's a lot more acceptable, because then it really is the length of the picture that corresponds with the quantities. Let's look at one more, and this is a big problem with bar graphs. Notice these 2 graphs here. These are 2 graphs from a poll about same-sex marriage rights taken in December 2008. And they look quite different, right? Which of these is misleading? The one that's misleading is this one. This is a bad graph. It's a bad graph because this vertical axis is condensed. It's condensed from 40 to 60, and so it creates a misleadingly large disparity, right? This bar now looks 3 times bigger than this bar, whereas if we actually look at it measured from 0, we can see that the difference is much smaller than this graphic would lead us to believe. So a teacher records scores on a 20-point quiz for 30 students in his class, and the scores are shown here. Let's try to create a frequency table for this data. And so we're going to create a chart, and we're going to have our data value and our frequency data. Now, this is no longer qualitative data, but it's now quantitative data, right? Because we're looking at numbers. But we're still going to treat it similarly. We're going to look at each score as our data, and then the frequency of that corresponding score. So maybe I'll even change this to say score. So for example, a score of 0. Looks like we've got 2 of those. How about a score of 5? Looks like we only have 1 of those. Kind of want to do this from smallest to biggest, so what's my next smallest number? Oh, looks like I got a 12 here, and I've got 1 of those. And then, let's see, next smallest, I've got a 15 here and another one there, so it looks like I've got 2 15s. And I would go down the line doing the same thing for each of the possible scores, and the resulting table would end up looking something like this. Now, it might be nice to create a graphical representation of our data. And so one option would be to try to create a bar graph like we did before, and that one might end up looking something like this. But this is somewhat misleading because these are numerical data, it's kind of weird to have 0 and 5 here and like 19 and 20 here. These are 5 apart, and these are only 1 apart. And so this isn't the best representation for this type of data. And so for that, we're going to need something called a histogram. Now, a histogram is very similar to a bar graph in that we're going to have, again, frequency along the vertical. I'm just going to write it up here, because there, frequency along the vertical. We can see here we're going to need to go up to 8. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. We'll do that. The difference is now the horizontal axis is also going to be a number line. So we have scores ranging from 0 to 20 here. So we'll go 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20. And of course, that should be nice and evenly spaced. And so now, for each of our score, we're going to create a bar. And when we create a bar, the value on the left side of the bar is included, but we're not including the value on the right side. So for example, for a score of 0, our bar will start at 0 and go up to 1. And so this is really a bar corresponding to a score of 0 here, which is on the left side of the bar. Different books and different software does this differently, but this is the approach that we're going to use. And so our next score here has a frequency of 1, but it has a score of 5. So it's way over here. There's a big empty space here in our graph corresponding to all those scores that never, didn't show up. Our next is a score of 12, also with a frequency of 1. And then we've got a score of 15 with a frequency of 2. And then a score of 16 with a frequency of 2. So this is going to start at 16 and extend up to, but not quite including 17. And then at 17, we're going to have a bar of height 4. And then 18, we're going to have a bar of height 8. It's about 8. And then at 19, we're going to have a score of 4. And notice that because we start at the value that's on the left, our score of 20 here with a height of 6 is actually going to start at 20 and go up to 21, even though we don't actually have any scores at 21, because this bar includes values starting at 20. And this is our corresponding histogram. Notice that we get a better idea of the overall layout of the data from this than we did from the bar graph. Now, suppose we've collected a lot of data, like 100 100 men's weights, as part of a nutrition study, and they range in value from 121 to a high of 263. For a total span of 142. And these scores might be all over the place. So we might have 100 different weights. And if we tried to create a frequency table for showing each individual weight and the frequency, we'd probably get a lot of frequencies of 1. In fact, almost all of our values would probably have a frequency of 1. And so what we're going to do is group the data into something called classes, or class intervals. And so this is going to be a range of values, and then we can create a frequency table based on the range of values. And so there's a lot of sort of decisions we have to make here, one of which is how many classes we want to have. And usually we want somewhere in the range of 5 to 20 classes, or groupings, depending upon sort of how much data we have or how big the data set is. And then oftentimes it's nice to have the ranges sort of start at nice values, though that's not necessary. But it is important that each interval be the same size. And so we could say, with our 142 values here, we would have a lot of options. Let's consider a couple. So, for example, I could have, let's see. So, I mean, like one option would be if I used 10 classes. Sorry, actually, let's do 14 classes. Then the width of each one would be around 10. So I could create a class like 100 to 129, and 130 to 139, and I'd end up with 14 classes that way. And so that'd be one option. I think I'm going to go for a slightly different approach here, and I'm going to make my classes a little wider. I'm going to use a class width of 15. So I'm going to start at 120, even though my data starts at 121, just because it's a nice number. And so my first class interval will be 120 to 134. My next one will start at the next value up, so 135 up to 149. Just as a point of clarification, if my data included decimals, like if people reported their weights as like 135 and a half, then this class would need to go all the way up to like 134.99 in order to cover those decimals. But we're going to assume, for the simplicity for now, that's not the case. And so my classes would continue developing something like this. So here's the rest of our class intervals, and then I put in some frequencies. Of course, this would come from the actual data. This would tell us that 4 students' weights were in the range of 120 to 134, and 14 students' weights were in this interval. And now that we have this, we can create our histogram. So our histogram here would start at, let's say, 120, and then maybe 135 and 150 and 165 and so on and so forth. And so our first bar here would have a height of 4, and would start at 120 and go up to, but not include, well, again, not include, so it goes up to 135, because we're going up to 135. My next category would have a height of 14, which I don't think I left enough room here for, so we'll just pretend 14, and extend out to 150. right? So it's including this entire range of values. Let me show you what this is supposed to look like. This is what that histogram would end up looking like, and this very nicely shows the distribution of weights. Now, some software doesn't let you put the values along the axis like this, and if that's the case, you can create a bar graph where the title of the bar is the range of values, and that does a pretty good job at capturing the same idea. If we have a set of class intervals and frequencies like we had for our weight data, one option for representing that was the histogram that we created. Another option would be to create a pie chart. We could do that by, again, calculating out relative frequencies. And these would be percentages, so we'd have to add our total number of frequencies and divide each of these by that to find a corresponding percentage. And then we could use that to create a pie chart. And that pie chart would end up looking something like this. And as you can tell, this is really hard to read, right? I mean, even if we were to put these labels directly on the pie chart, this is probably not a particularly useful representation of the data, certainly not in comparison to, say, our histogram that we had earlier. And so, when you have a large number of categories or classes, doing pie charts is probably not the best idea. So sometimes we need to compare two different groups of data. And so, for example, this data comes from a task in which the goal is to move a computer mouse to a target on the screen as fast as possible. So you have to move the mouse and click on a target. And it was done twice with a small rectangle and a large rectangle, so for two different targets. And we've collected frequency data and we've created class intervals, each of width 100 milliseconds. And so this is our data. And so to create a graphical representation, one option would be to create histograms of each of these data on top of each other. This is called a comparative histogram, and it would look something like this. Now, this particular graph is done as a bar graph, where the class intervals are the bar labels, and that's mainly because of the limitations of the software I was using. But you can see that the lighter blue here is representing the times for the small target, and the darker reddish color, purple color, is showing the times for the large target. And we can start analyzing the behaviors here using a graph like this. For example, we can tell that the large target scores seem to sort of on average be smaller, and that they tend to be more clustered, whereas the small target scores tend to appear to be more spread out. Now, this is still not a great representation of the data, and so another option here would be something called a frequency polygon, frequency polygon. And the idea is basically the same, except we put a dot at each interval, basically at the same height that the histogram would be. And then we sort of connect the dots. Now, this is a little misleading because we're not suggesting that this actually, increases that way, but it gets the idea of trend perhaps a little bit more than the histogram does, and this is what that ends up looking like. Now, this again sort of gets that idea that the large target values are a little smaller, and a little more compact, whereas the small target scores are a little more spread out and appear to be slightly larger. So next we're going to talk about numerical summaries of data, and we're going to look at a few of them. First, we're going to start with measures of what's called measures of center. Now, you may have heard of averages before, and we try to avoid to use the word average in statistics because it's a bit ambiguous. And instead, we're going to use the word mean, the arithmetic mean, more specifically, which is what we're going to use to calculate what you've probably heard called average before. And so the mean we calculate by finding the sum of the scores and dividing by the number of scores. So the mean is simply this, sum of scores. So there's our sum of scores, and we're going to divide it by the number of scores. We have 4 scores here. And pulling out my calculator, I get 85.25, so we can say that Marcy's mean exam score is 85.25. Let's look at another one. Here's the number of touchdown passes thrown by each of the 31 teams in the National Football League in the 2000 season. And we could find the mean number of passes thrown. So if we're going to do that, we're going to need to add all of these up. So we're going to find this plus that, plus that, plus that, plus that, plus that, so on and so forth. And it turns out those add up to 634. Then to find the mean, we're going to take that sum and divide it by how many scores there are. There's 31 different counts here. And we divide that, and we get 20.4516. Now, it would be appropriate here, because all of this data has no decimal places attached to it, it would be appropriate here for us to round this to 1 decimal place. It's common to round means to 1 decimal place more than the data originally had. So it would be most correct here for us to say the mean number of touchdown passes thrown in the NFL season in the 2000 season was 20.5 passes. But it's certainly not uncommon to hear the word average used in place of mean, at least in common language. So in addition to the mean, another measure of center is called the median, and we'll get to the actual question here in a second. So the median is the middle value from a set of data. And so, for example, middle value in order. So if we list our data in order, the median will be the middle value. So if my data was 1, 3, 7, 10, 15, the middle value would be 7. 7 would be the median of that data. If my data was 1, 3, 7, 8, 10, 15, notice now the middle is right between 2 values. And so when that happens, we find the mean of those 2 values. In other words, we add them up and divide by 2. And we get 7.5 as the median. So if we have an odd number of data, then the median will be fairly easy to find. It will be in the middle. And if we have an even number of data, then we're going to need to split the difference. Now, the way that we can find where the median is using something called a locator. And so we're going to take the number of data. In this case, we had 5 pieces of data, and we're going to divide it in half. So 5 divided by 2 is 2.5. Now, if this number comes out to be not a whole number, which will happen whenever we have an odd number of data, then we go up to the next whole number up. So it's going to be the third piece of data. Third piece of data, right? So in our order, 1, 2, 3, third piece of data. In this case, 6 divided by 2 is 3. And so this already is a whole number. When that happens, then we find the mean of, in this case, the third and fourth. So we start at the third value. So we find the mean of the third and fourth pieces of data. But for small sets of data, you can use this visual approach, which usually works pretty well. So here we have a set of data. I have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 pieces of data. So we use the letter n to represent the number of data. And so this is the even case, right? So I can say 10 divided by 2 is 5. And so we're going to need the mean of the 5th and 6th data values here. But most importantly, we first need to put our data in order from smallest to biggest. Or biggest to smallest, doesn't really matter, but I'm going to go small to big here. So we got 2, 4, 5, 5, 6, 7, 7, 8, 8, 10. Let me double check I got everything. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 pieces of data. Good. And really you can see that this point here splits the data in half. This is the 1, 2, 3, 4, fifth piece of data. So the fifth and the sixth piece of data here we need to find the mean of. 6 plus 7 divided by 2 is 6.5, and so that is our median of this data. So let's look at another example. So here is a set of touchdown passes, and this time they've been arranged in order for us, which is awfully nice. And so notice there are 31 pieces of data. If I divide 31 by 2, I get 15.5, which is a decimal value, and so I go up to 16th data value. Right? Because we have an odd number of data, we know that the median is going to be a single value. So now I can just find the 16th piece of data, because it's already listed in order. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16. So my median is 20. So here again is our income data from 100 families. We have income and frequencies here, so we're working off of a frequency table. So we have here 100 pieces of data. So that's even, so we know that the median will be in between the, in this case, 50th and 51st piece of data. Sorry, piece of data. Okay, so between the 50th and 51st piece of data. So now we need to figure out where that is. So our first 6 pieces of data are here. So we've counted up 6 pieces of data so far. And then we have another 8 pieces of data here. So altogether, that would be 6 pieces of data there, 8 pieces of data there. We've now counted up to 14. So together, these make 14 pieces of data. So we have 14 pieces, and then we add in 11 more, and now we have a total of 25 pieces of data. So all of these together is 25 pieces of data. And then let's see, if we add in another 17, that's going to get us up to, let's see, 42. And so altogether, this is 42 pieces of data. And then add that to 19, and that gets us up to 61. And so altogether, this is 61 pieces of data. So now that we're up to 61, we've passed 50 and 51, which means where were pieces of data 50 and 51? Well, they weren't here. They weren't up to 30, which means pieces of data 50 and 51 must have been here. And so both the 50th and 51st pieces of data were 35,000, and the mean of 35,000 and 35,000 is also 35,000. And so here the median income in this neighborhood is 35,000. Now, interestingly, look what happens when we add another family. So we're going to add another family to our mix here. Again, we're going to add this family who makes $5 million a year. So now we have 101 families, and from that we know that the median is going to be a single value, in this case the 51st value. And just like we did before, we can start counting up from the bottom. And since the bottom part of the data didn't change, we already know that the 51st piece of data is in this category, and so the 51st piece of data is 35,000. So notice that with the median median income in this neighborhood has not changed with the addition of this very rich family. So this is one of the features of the median, is that it is not swayed by outliers nearly as much as the mean is. When we have quantitative data, numerical data, we usually find the mean or the median of the data. That's usually the most useful measure of center. However, when we have categorical data, like these car colors with corresponding frequencies, then finding numerical measures isn't possible. And so for that, we have something called the mode. The mode is another measure of center, and it is a measure of the most typical value in the set. In other words, it's the value that shows up the most often. And for that, we simply look at our frequencies here and say, that's my biggest frequency. And so the mode here is green. Green is the color that shows up the most often.